Here's our lecture today, the dot product in Rn. So let n be a positive integer. Generally, we pick n to be 2 or higher, but it could be 1 as well. Let x hat be a vector in Rn with entries x1 all the way up to xn. And vector y hat in Rn be the vector whose entries are y1 all the way up to yn. The dot product of x and y, x hat dot y hat, is the quantity x1, y1, so x1 times y1, plus and so on up until the very last product, xn times yn. So the dot product of vectors x and y is a constant, a real constant. It could be positive, it could be 0, it could be negative. It's a real number. First question to ask, the first question we should ask, is the dot product commutative? Second question, does the dot product distribute over addition of vectors in Rn? The answer in both cases is yes. Let's write that as a lemma. Lemma. The dot product in Rn is commutative. And the dot product in Rn distributes over addition of vectors in Rn. So the dot product in Rn distributes over addition of vectors in Rn. Let's prove the second property and leave the verification of the first property as an exercise. And that will be very simple. You just have to observe that each of the terms has a product of real numbers, so you just have to commute them. At the end, you will realize your first property. Okay, so let's prove that the dot product distributes over addition of vectors in Rn. So here is what we want to show. Pick 3 vectors in Rn, x hat, y hat, z hat, show that the dot product of x hat in the sum of y hat and z hat equals to the dot product of x hat and y hat plus, this is addition of real numbers, the dot product of x hat and z hat. Alright, so we proceed. Let's use entry notation for this proof. So I'm going to write this expression using entry notation. So I will have x1. Typical entry will be xi. All the way up to the last entry, which is xn. Dot. Now I want the sum of vectors y and z, and we have a definition for that. So let me put a parenthesis here and tell what the sum is. We know what the sum is. So if we use entry notation, this vector y hat will be y1 dot 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 yi dot 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 yn, and the vector z will be z1 dot 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 zi dot 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 zn. So what happens when you add them? You get the following: y1 plus z1 comma dot dot dot. The typical entry will be yi plus zi dot 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 up until the last entry, which will be yn plus zn. So yn plus zn. Now let me remove the parentheses. It is actually not required because this is the result of that sum. I skipped a step here. I should have written y in entry notation, z in entry notation, and then my next step would have been this one. Now, what's the dot product? I have to multiply x1 times y1 plus z1 plus dot 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 plus, the typical entry will be xi multiplied by the quantity yi plus zi plus dot 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 plus the very last entry will be xn multiplied by the quantity yn plus zn. Now, let's observe that each of these terms consists of real numbers. So we use the fact that the multiplication of real numbers distributes over addition of real numbers. So we're going to do that on each term that appears here. So I'm going to multiply x1 y1 plus x1 z1, and then plus da 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 plus xi yi plus xi zi plus da 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 plus xn yn plus xn zn. Let me make space for that and write it. Equals x1, y1 plus, let me put that under the other term, let me put it under x1, z1 plus dot plus xi, yi plus xi, zi plus dot, and then we get our last result, which is xn, yn. So plus xn, yn plus xn, zn. At this point, we step back and look at each of these rows and then realize that the first row represents the dot product of x hat and y hat, and then plus, this is a addition of real numbers, so plus, and then the second row represents the dot product of x hat in z hat. And that completes that proof. Okay, let's continue. Let's now define what the norm of a vector in Rn is. So this is our definition. This is a definition. So the norm of a vector in Rn, norm of a vector in Rn. So let's start with the vector in Rn. Here again, the variable n, it represents a positive integer, generally 2 or higher, but it could even be 1. So let x hat be a vector in Rn. The norm of x hat, which we will notate this way, the norm of x hat. So there are two parallels surrounding x hat, but you pronounce the norm of x hat, or the norm of x if you don't like saying hat, is given by the following formulation. The norm of x hat is the square root of the dot product of x hat with itself. What is it then? So you're taking the square root of x1 times x1 plus dot plus xi times xi plus dot plus xn times xn. That's what it is. It is defined because when you look at the terms of this dot product, none of them are negative. So when you add non-negative numbers, you get a non-negative answer. So whatever we are taking the square root of in here is not negative, so this is defined. It is a real number. Okay, so let's do a very simple example. Let's find the norm of a vector in R2. So example. Let vector x be the vector in R2 which has entries 3 and -4. Find the norm of x. This is a very simple example. So by definition, so here's my solution. So by definition, the norm of x is the square root of x hat, excuse me. And that's simply the dot product of 3, -4 with itself. So we end up with 3 times 3, which is 9, plus -4 times -4, which is 16. So that's the square root of 25, which simplifies into 5. Very simple example. Okay, here is an observation. If you think about it, this norm found some number which represents certain aspect of the vector. The aspect that is representing is the length of that vector. So if you work out the norm of a vector in R3, it will also represent the length of that vector in R3. So in general, when you talk about the norm of a vector in Rn, that's just a generalization of the length of a vector in R2 and R3. So you might hear, what is the length of the vector x hat equals 1, 2, 3, 4, 5, all the way to like n. So that will be just the the square root of the dot product of the vector x with itself, and that's the end of that. All right. Let's write down a theorem, various properties of the norm. So the first property is that the norm of a vector is a non-negative value. Also, if you find that the norm of a vector is 0, that means that the vector is the 0 vector. So that's one property. Another property, if you find the norm of the scalar multiplication of a constant and a vector in Rn, if you find the norm of the scalar multiplication of a constant and a vector in Rn, what you will get is the following: the absolute value of the constant times the norm of the vector. Another property, if you take the absolute value of the dot product of two vectors x hat, y hat, if you take the absolute value of that dot product, that is going to be less than or equal to the norm of the first vector times the norm of the second vector. That is known as the Cauchy-Schwarz inequality. And one more property. If you find the norm of the sum of two vectors, x hat plus y hat, that is less than or equal to the norm of x plus the norm of y. Alright, that one is known as the triangle inequality. Let me try to write all those properties here on this small board, and we're going to prove some of them on the main board. Okay, so this is a theorem. There are 4 parts to it. So my hypotheses are that n is a positive integer, that x hat, y hat, x hat, y hat are vectors in Rn, and that a is a real number. So here's my first property. The norm of x hat is greater than or equal to 0. If x hat equals 0, that implies that x hat if x hat equals 0, that implies that x must be the 0 vector. So that's our first property. Second property. The norm of the scalar multiplication of a and x hat, remember a is a real constant, x hat is a vector in Rn, that's equal to the absolute value of the constant a multiplied by the norm of x hat. Third property. The absolute value of the norm, the absolute value of the dot product of x hat and y hat is less or equal to the norm of x hat multiplied by the norm of y hat. This is an inequality and it is called the Cauchy-Schwarz inequality. Cauchy-Schwarz inequality. And our last property here, oops, it will be 4, property 4. The norm of x hat plus y hat is less than or equal to the norm of x plus the norm of y. And this inequality is called the triangle inequality. Let's prove two of these properties. So let's prove one, which has two parts to it, and let's prove 3. Properties 2 and 4 are exercises. Okay, so let's try this first. So let x hat be an Rn. With x hat equaling the vector whose entries are x1, xn. By definition, the norm of x hat is simply the square root of this vector dot with itself. So it's x1, xn dot product with x1 etc. xn. So what do we get? x1 squared plus x2 squared plus dot 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 plus yn squared. So each of these terms are perfect squares, or squares of some real number, excuse me. Not necessarily perfect squares, but squares of real numbers. And what you have to observe here is that none of those terms can be negative because they're squares of real numbers. So this ends up being greater than or equal to 0 because xj squared is greater than or equal to 0 for all xj in R, for j equals 1 through n here. Okay, so that was simple. Now let's suppose that you know that the norm of x is 0. So suppose the norm of x is 0, but that x weren't the 0 vector. Suppose that the norm of x were 0, but x weren't theta. Suppose that. In other words, suppose that you can get the norm of x to be 0 without x being the 0 vector. Okay, so well, if x is not the 0 vector, that means at least one of its entries must be different than 0. So if x equals x1 and so on xn, since x is not theta, at least one of these entries cannot be 0. So if x equals that, there is some, let's call it xi, different than 0 amongst the entries of x. So then what happens when you find the norm of x? So then the norm of x hat will be the square root of x1 squared plus dot 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 plus xi squared plus and so on plus xn squared. Remember we said that xi, we're taking xi to be different than 0. So what happens here is that this is greater than or equal to, if I drop all the terms except xi squared, then whatever quantity I get must be lesser than the one that had all the terms. Because remember, none of the squares that you see there can be negative. So if you drop anything from there, the result is going to be equal or smaller than the original one. So at the end, I just get that the result norm of x hat is greater than or equal to the square root of x I squared. That's just this absolute value of xi. But since we're assuming that xi is not 0, that has to be greater than 0. And we have reached a contradiction to our hypothesis that says that the norm of x hat is actually 0. Here we're saying it turned out to be greater than 0. This contradicts that. So, conclusion, we reject the possibility that x is not theta. So therefore, x must be theta. If you assume it is not theta, you get the conclusion that the norm of x hat is greater than 0, contradicting the hypothesis that says it is equal to 0. Okay, now let's begin our proof of the Cauchy-Schwarz inequality. And for this, we have to apply a certain trick of sorts. So here we go. Proof of 3. Let's consider the following dot product. The dot product of ax hat plus by hat with itself. We have that the dot product distributes over vector addition, so we can do the usual first, outer, inner, last here, because the distributive property holds. When we do that, here's what we're going to get. A squared x hat dot x hat, which is the norm of x hat, plus, now let's do this part, b times b is b squared, and then y hat is going to be the norm of y hat squared, here also squared. So x hat dot x hat, what is x hat dot x hat? If you take the square root of that, that gives you the norm of x hat. But if you don't have a square root, then you must have the norm of x hat squared. And similarly for y hat dot y hat. Okay. And then what else? Here you're going to get a b x hat y hat dot a x hat dot y hat. And then over here you're going to get BA, which is the same as AB, and then y hat dot x hat, but remember that dot product is commutative, so that's the same as x hat dot y hat, so you just get another one of this. So let's just insert a 2 there. Okay, now you have to realize that this itself is this is the norm of, this is the norm squared. What you're seeing right there is the norm squared of ax hat plus by hat. Therefore, this is a non-negative number, so that turns out to be greater than or equal to 0. Okay. Let me consider the norm of ax hat minus by hat. I'm going to pretty much go do the same thing, but now I'm finding the dot product of ax hat minus by hat with itself. I said it at the beginning, there is a trick involved. I'm developing that trick right now. Just follow what I'm doing. Now this is the norm. This is the norm of ax hat minus by hat square, right? Squared. So it is greater than or equal to 0. Now I got to figure out what that dot product was. What was it? Well, is a squared the norm of x hat squared? Excuse me, here I have to put a minus. I meant to say both are minuses here. That's an error. Sorry about that. So negative times negative is positive. B times B is B squared. And then y hat dot y hat is the norm of y hat squared. And then here I get minus AB x hat dot y hat. Again, commutative property will apply, so that's also the same thing, minus AB x hat dot y hat. So I'm going to get minus 2 AB x hat dot y hat. Okay, so those are my two norms. One of a x hat plus by hat is squared, and a x hat minus by hat norm squared, the norm of that squared. So let me extract what I want from there. I want to say that this quantity is greater than or equal to 0, and similarly in the second line I want to say that this quantity is greater than or equal to 0. That's the part I need from that analysis. So let me erase all this. This quantity is greater than or equal to 0. Same with that other quantity. Okay, we haven't talked about A, B. They're constants, but I want to make a choice for them. I'm gonna call. I want to make A the norm of y, and I want to make B the norm of x. So let's declare that they're constants, but I want to pick them. So let A equal to the norm of y, comma B equals, let B equal to the norm of x, excuse me, y hat x hat. So by substitution, here's what I'm going to get in my first inequality. I'm going to get that 0 is less equal norm of y squared, norm of y squared, norm of y hat squared, multiplied by the norm of x hat squared, plus what? Pretty much the same thing, right? Except that it's in reverse order. So this is the norm of x squared multiplied by the norm of y hat squared, plus, now remember that A is the norm of y hat, B is the norm of x hat. So it's plus 2. If I commute them, I get 2 times the norm of, let me write here so that you don't forget that. This is the norm of y hat. That's the norm of x hat. But I'm going to commute them. So I'm going to put the norm of x hat first and the norm of y hat last. And that's x hat dot y hat. Don't forget that. That's still there. Okay. Let me move this a little bit down. So 0 less equal. I'll write it afterwards. Right now, let me erase it. I'll write it. I won't forget that there is a minus here instead of a plus. But it's pretty much what you see in there, but with a minus. Okay. This became two of the same, right? So 0 is less equal to, when you commute these two, you get identically that. So that's the norm of x hat squared multiplied by the norm of y hat squared, but there are two of them. So put your 2 in front. And then plus 2 times the norm of x hat multiplied by the norm of y hat times the dot product of x hat and y hat. Now, let's make the assumption that neither norm of x hat nor y hat is 0. Then I can divide both sides by the norm of x hat, y hat. So there is cancellation. This goes completely away. You can actually get rid of the 2 also. So let's also divide by 2. So the 2 x hat, y hat, the 2 norm of x hat, norm of y hat completely cancel. So you are in the second term, you get the dot product of x hat and y hat. In the first term, the 2 cancels entirely, but one of the norms of x hat and one of the norms of y hat remains. So 0 is greater is 0 is less or equal to the norm of x hat multiplied by the norm of y hat plus the dot product of x hat and y hat. All right, so that's the end of my first inequality. Now my second inequality, let me put the minus, excuse me, let me go here. Let me put the minus in there. I will get 2 of those, but let me write everything again. So remember, in the second inequality we had this, 0 is less or equal to, I believe I left it in this form, but there was a minus here. Let me put the minus there, let me put the 2 in there, let me put the x hat dot y hat, but let's immediately make the substitution. We have this same expression with the minus here, but I'm making the same substitution for a and b. So that will give you the norm of y hat squared multiplied by the norm of x hat squared, and then plus the norm of x hat squared multiplied by the norm of y hat squared, and then minus 2 times a, which is the norm of y hat, times b, which is the norm of x hat. The same manipulation as before will give you the following. Same manipulation, except there is a minus here. So this becomes 2 times the norm of x hat squared, the norm of y hat squared. That's the end result of those first 2 terms. And here you just get pretty much the same thing. I'll put the order I'll put this product in reverse order. So I get the norm of x hat times the norm of y hat, and then the dot product of x hat and y hat. I get to divide both sides of the equation by 2 times the norm of x hat times the norm of y hat, and that will give me this end result. 0 is less or equal to, so what survives here is the norm of x hat multiplied by the norm of y hat, minus the only thing that survives here is the x hat dot y hat. And notice that these 2 inequalities will lead to a compound inequality. So let me write that. In order to write that compound inequality, I will need to make some space on top. So let me write this one first. So here I get that the dot product of x hat, y hat, if I move it over there, is less or equal. Let me see if that's what I want to do. Give me a minute, please. Yes. All right. So that's what I want. So I moved this expression to the left, so it became positive. So x hat dot y hat is less than or equal to the norm of x hat multiplied by the norm of y hat. Now over here, what I get is the following. I get that let me see, I want, which one do I want here? I want to solve for this now here, so this time I want to move this. Let me write this on the left side. So for this one, actually let me leave it there. So here I want that x hat dot y hat is greater than or equal to, let me move that one to the left, the negative of the norm of x hat multiplied by the norm of y hat. Okay, so here's my compound inequality. The dot product of x hat, y hat, on the one hand is less than or equal to the norm of x hat multiplied by the norm of y hat. And at the same time, that's greater than or equal to the negative of that. What is this? This is saying something. This is saying that if you take the absolute value of this expression, remember this is some real number, if you take the absolute value of that real number, the absolute value of that real number is going to be less than or equal to the norm of x hat multiplied by the norm of y hat. And that was what we wanted to prove. And I think that is all I needed to show in this lecture. So thank you for watching. Very long lecture.